In this video, we're going to talk about calculating the molar enthalpy of solution as well as neutralization calorimetry. So for this first example here, how you know that this is a molar enthalpy of solution type question is if you're getting an ionic compound and it's just dissolving in water. So the first thing that you're going to want to check is to make sure that your ionic compound is soluble in water. But before I get into how to do that, let's just write this as a little note just to help you identify when you have a molar enthalpy of solution type question. So these are going to be identified when you have an ionic compound that breaks apart into its ions if it is soluble in water. Okay, so for our example, we're given 4.24 grams of lithium chloride is dissolved in 100 milliliters of water. So for checking if your compound is soluble in water or not, how you would check that is you would go to page 6 of your data booklet. And since we were given lithium chloride, first we're going to look for the anion, so the negative ion, which is going to be chloride. Then we're just going to trace our finger down. Now it says most cations are going to be soluble with chloride, but we just want to keep on going and make sure if our cation is in our list of exceptions here. Okay, so since lithium is not in our list of exceptions, that means it does fall under most, so that means it is very soluble. Okay, so let's just continue reading this. So 4.24 grams of lithium chloride, which is in fact soluble in water, is dissolved in 100 milliliters of water at an initial temperature of 16.3 degrees Celsius. The final temperature of the solution is 25.1 degrees Celsius. Calculate the molar enthalpy of solution for lithium chloride, and it also wants us to give a thermochemical equation there. Okay. So, as a little reminder here, to find molar enthalpy of solution, so we'll say RH, you're going to need a few things here. So, you are going to need moles of your substance in order to figure out your molar enthalpy of solution for lithium chloride. Okay. Now, let's get started on that there. Okay, another thing that I'm going to want to figure out is the change in temperature, just for later. So I'm going to start off by figuring out change in temperature and moles of lithium chloride. So change in temperature is equal to final minus initial. So our final was 25.1 degrees Celsius. Minus our initial temperature was at 16.3 degrees Celsius. So 25.1 subtract 16.3, that's going to give us positive 8.8 degrees Celsius. Okay, so what this means is the solution increased in temperature when lithium chloride was dissolved. Okay, so what that means is when lithium chloride dissolves in water, that's going to be an exothermic process. And we know that because water gained energy, or it increased in temperature, when lithium chloride was dissolved. So if your surroundings, such as water, gain energy, you know that's an exothermic process. If your surroundings lose energy, then it's going to be an endothermic process. Okay, I also said we wanted to find the moles of lithium chloride, so we're going to get rocking and rolling on that. So moles is equal to mass divided by molar mass. So our mass was 4.24 grams of lithium chloride. The molar mass for lithium chloride, you calculate this by looking at your periodic table, but that's going to be 42.39 grams per mole. So if we divide those two numbers, 4.24 divided by 42.39, we're going to get 0.10002, goes on forever. So this is the moles of lithium chloride. Okay, so as a reminder, just for the game plan for our formula, remember that the heat lost by your system is going to be equal to the heat gained by the surroundings. Okay. So heat lost by the system, that's going to be negative EP. We put the negative on the left-hand side just because it is an exothermic reaction. It's equal to our kinetic energy of water. So I'm actually going to color code these. So anything that's blue is going to relate to water, and anything pink is going to relate to lithium chloride. Okay, so I'm just going to expand both of these terms on the left and right hand side of our equation here. So just as a reminder, potential energy is equal to the change in enthalpy, which is equal to moles times the molar enthalpy of reaction. So this is for all for lithium chloride. And as a reminder, kinetic energy can be expanded as mass times specific heat times the change in temperature. Okay, so since we're looking for molar enthalpy, we're looking for this term. So I'm going to isolate it just by dividing by negative moles. So our molar enthalpy for lithium chloride is going to be equal to mass times specific heat times the change in temperature divided by negative moles of lithium chloride. So this is going to be the formula that we're using here. Okay, so for our mass of water, they only give us a volume 100 milliliters, but remember that 1 milliliter is equal to 1 gram of water. So 100 milliliters is just 100 grams of water. Now the specific heat of water, if we look at our data booklet and go to page 3, specific heat of water is 4.19 joules per gram degree Celsius. And then our change in temperature for water was at 8.8 degrees Celsius. And then our moles of lithium chloride was at 0.1002, goes on forever. So grams and degrees Celsius cancel out. So putting this into my calculator, I'm going to go 100 times by 4.19 times by 8.8 divided by negative, and then our answer for the moles, so that the reason why I'm doing that is so that I get that entire number that I just calculated above this entry. So then our answer is going to be negative 36,863.30377. Now for our units, the only units that didn't cancel out are joules and moles. Now since all of the numbers given to us were in 3 sigdigs, we need to make sure that our final answer here is in 3 sigdigs. So I count from the left, 1, 2, 3. There's my cutoff line. So since our cutoff line is ahead of the decimal point, we're going to need to use scientific notation. So I need to move the decimal over so that there's only 1 digit to the left of it that is not 0. So 1, 2, 3, 4. Okay, alternatively, if you did want to use kilojoules per mole so that you wouldn't have to do scientific notation, then your answer would be negative 36.9 kilojoules per mole. Okay, so again, what I'm doing to convert from joules per mole to kilojoules per mole is I'm just dividing by 1,000. Okay, so this number here, that tells us the molar enthalpy specifically for lithium chloride. And the reason why I want to know this is because in our thermochemical equation, we don't use molar enthalpy, we use change in enthalpy, because change in enthalpy refers to the entire reaction, not just a specific substance. Okay, so again, coming back to this formula right here, how we figure out change in enthalpy is we times moles by the molar enthalpy. Now, since in this previous calculation here, we've already taken into account that we used 4.24 grams of lithium chloride, where we're going to get the moles from is from the coefficients of the balanced chemical equation. So I want to first start off by writing the balanced chemical equation for this thermochemical equation. And what turns it from a chemical equation to a thermochemical equation is the addition of an energy term. So remember, this is all about lithium chloride being dissolved in water. So I'm going to write it as lithium chloride. Okay, and we're putting it in water, so I'm writing it as aqueous, and the whole point of this is to just show that it's splitting apart into its ions here. So remember, whenever you're writing a dissociation equation like this, and you're splitting an ionic compound into its ions, you're only ever going to get two products, the cations, or the positive ions, and the anions, or the negative ions. Okay. Now, this reaction's already balanced here, so I can see that we're using 1 mole of lithium chloride. So I'm going to have to do this off to the side here. But our change in enthalpy is equal to 1 mole, so this is coming from the coefficient for lithium chloride. So this is just short for coefficient. Okay, and then I'm just going to choose to use the kilojoules per mole. So then our moles are canceling out. And this will give us negative 36.9 kilojoules. Okay, so again, the purpose of this type of calculation is to show that you understand that you don't use molar enthalpy when you're trying to represent the change in enthalpy. So mathematically, you do got to show this work, even though the number didn't change because we multiplied it by 1, but the units did change. Okay, so we're going to use this in our thermochemical equation. Remember that the negative represents that this energy is being lost by the system. So another way to say that is energy is being produced by the system because it's an exothermic process. So we're going to take that and put it on the right hand side, and you always write plus. So your energy term should never be negative when you write it in your thermochemical equation. So plus, and then 36.9 kilojoules. Alright, so let's move on to neutralization calorimetry. So all that is when you have an acid and a base reacting, that's all a neutralization reaction is. So the general template for a formula that we're going to use is this. Now, the reason why the negative is on the left-hand side of the equation, so typically where the like this term talks about the substance undergoing a chemical reaction, and whenever we have a neutralization reaction happening, it's always going to be exothermic. So let's just write that as a little note. Okay, now with this formula here, once again, like, this isn't in your data booklet, so you are going to have to memorize it. Basically, any formula that we do talk about, you are going to have to memorize it because there's not much in the way of formulas given in your Chemistry 30 data booklet. So, with this, for our potential energy side, we're going to be calling this, or the substance that these terms relate to, we're going to be calling them the reference substance. So it's specifically the substance that the question's asking you about. Okay, so I'm just going to call this the reference substance. And now over here we have two kinetic energy terms. Okay, so one is going to be your solution 1, which could be your acid or could be your base. Just arbitrarily, I'm going to call this our acid. And then the second solution is just going to be our base. Now, most solutions in this course are aqueous, therefore water makes up a large component of this. So what this means you can do is you can assume that the specific heat capacity both for your acid as well as for your base are going to be 4.19 joules per gram degrees Celsius. Now, as another reminder here, if a volume of a solution is given, again, mostly because it's water, you can assume that 1 milliliter of your acid or of your base is going to equal 1 gram of either your acid or your base. It just depends on what you're talking about there. Okay, now you can calculate moles using volume and concentration. Now, as a reminder here for that, your moles is going to be equal to concentration multiplied by volume. That's going to be the formula that we're using. Again, yet another formula you do have to memorize because it's not given to you in the data booklet. Okay, and this symbol right here just stands for the molar enthalpy of neutralization. All right. For our first example here, we have a student mixed 100 milliliters of 1.50 mole per liter sulfuric acid with 200 milliliters of 1.5 mole per liter sodium hydroxide solution. Both solutions were at 19.7 degrees initially, and the highest temperature reached was 34.1 degrees Celsius. Calculate the molar heat of neutralization for the sulfuric acid solution. Okay, so since this is the specific substance that we're being asked about, this is going to be our reference substance. So that's going to be the part that we care about that ends up on the left-hand side of our formula. Okay. So we're going to want to find the moles of this substance. All right, so we know we need to find moles of this substance here. So that means we're going to be using this equation. Now, as a reminder, this is a formula you would have used in Chem 20. N stands for moles, C stands for concentration, which is in moles per liter, and volume is going to be in liters. Okay, so I'm noticing here that in order to find moles of sulfuric acid, like here's the volume and here's the concentration of sulfuric acid, notice that they've given us volume in milliliters and we need liters. So all that means is we just need to divide by 1,000 in order to convert 100 milliliters into liters. So the formula for sulfuric acid is H2SO4. So our concentration was 1.5 mole per liter, and 100 divided by 1,000 is just going to be 0.1 liters. So our liters cancels out. And 1.5 times by 0.1 is going to just give us 0.15. That's moles of sulfuric acid. Okay, the other thing that I want to figure out before I get into using this formula here is just the change in temperature. So that's final minus initial. Now it does say that initially we were at 19.7 and then the final temperature was 34.1. So then that's going to give us positive 14.4 degrees Celsius for a change in temperature of both the acid and the base. So again, because a neutralization reaction is an exothermic process, that means that our system is going to lose heat, but the surroundings is going to gain the heat. So we're going to have the negative, I'm going to change that color there, negative EP, so the negative goes on this side because it is an exothermic reaction, and this is for sulfuric acid specifically, because that was our reference substance. Okay, and then our heat gained, remember we have two kinetic energy terms, one belonging to the acid and the other one belonging to the base. So I'm just going to go purple for acid, and then blue for base. So now I'm just going to expand all of these terms. So moles times the molar enthalpy of neutralization for sulfuric acid is going to be equal to mass times specific heat times change in temperature of the acid plus mass of the base times the specific heat capacity of the base times the change in temperature of the base. So we're looking for this term to be isolated, so we need to isolate it by dividing by negative moles. So remember, anything pink has to do with sulfuric acid, anything purple has to do with our acid, which is sulfuric acid, and then anything blue has to do with our base. which is sodium hydroxide. All right, so our mass of sulfuric acid is going to be this 100 milliliters. But just as a reminder, 1 milliliter is equal to 1 gram. So this is going to be 100 grams of our sulfuric acid times by the specific heat capacity of both our acids and our bases. Since they're mostly made up of water, they're going to have the same specific heat capacity as water. And then our change in temperature was 14.4. All right, for our base, we had 200 milliliters. So that's going to be 200 grams times by 4.19 joules per gram degrees Celsius times by 14.4 degrees Celsius. And then our moles for sulfuric acid was 0.15. So how I'm going to be entering this into my calculator, I'm going to want to double bracket the numerator. Okay. Just so that it's very clear to my calculator what's in the numerator and what's in the denominator. Okay. Okay, I'm going to bring up my last answer so that it's clear what I'm putting into my calculator for the denominator. So 100, double bracket that, 100 times by 4.19 times by 14.4, close that bracket, plus, so now I'm talking about the base, 200 times 4.19 times 14.4, close the bracket and then close the outermost bracket, divide by our negative 0.15, and there's our answer. Okay, so negative 120,672. For our units, that's just going to be, grams are canceling out, so our degrees Celsius, so this is going to be in joules per mole. So it looks like the least amount of sig digs that we have to work with is 3. So I count from the left, 1, 2, 3, there's my cutoff line. So because it comes in front of the decimal, which would be right here if I wrote it, we need to use scientific notation. So then that'd be 1, 2, 3, 4, 5 spots that I need to move the decimal. So my answer for the molar enthalpy of neutralization of sulfuric acid specifically would be negative 1.21 times 10 to the power of 5 joules per mole, or if you really wanted to talk about this in terms of kilojoules per mole, you just divide by 1,000. So that would give you negative 121 kilojoules per mole. So you could do either or. The reason why is because the question didn't specify what units it wants the answer in. So just as a reminder, this is the molar enthalpy of neutralization for sulfuric acid specifically. Alright, part B asks us to calculate the molar enthalpy of neutralization for sodium hydroxide. So now our reference compound here, or our reference substance, is sodium hydroxide. So we need to find the moles of this. So again, we're using moles as concentration times by volume, concentration being in moles per liter, volume being in liters. So we're given 200 milliliters of sodium hydroxide. To convert 200 milliliters to liters, you just divide by 1,000, so that's going to give you 0.2 liters. So 1.5 times by 0.2 is going to give us 0.3, and that's the moles of sodium hydroxide. Now for the change in temperature, since it's talking about the same reaction, our change in temperature is still 14.4 degrees Celsius. Okay, so I really don't need to calculate that over again. I can just write positive 14.4 degrees Celsius. Okay, so what I can do now is we can essentially use this equation over again. The only difference is that our reference substance is sodium hydroxide and not sulfuric acid. So this N just means for neutralization. So this MC delta T is for the acid. And the blue MC delta T is for the base. Okay. Now, the calculation is going to be very similar to what we just did, okay, except for when we divide by our moles, we're going to be dividing by this 0.3. Alright, so now our answer is negative 60,336 joules per mole. Okay, and again, we're still doing this in 3 sig digs. So if I count from the far left, 1, 2, 3, there's my cutoff line. So we're going to have to use scientific notation. So it's going to be negative 6 point, and actually I should draw this out. So I'm moving the decimal over 1, 2, 3, 4 spots to the left. So negative 6.03 times 10 to the power of 4 joules per mole. But if you really wanted to put this in kilojoules per mole, which you can do because the question doesn't specify units, if you divided this by 1,000, it would just be 60.3, and then your units would be kilojoules per mole. Okay, so if you want to do joules per mole or kilojoules per mole, either is fine when the question doesn't specify the types of units it wants. However, just pick one. You're not expected to do both. So molar enthalpy for sodium hydroxide specifically. All right, so last but not least, we have to write a thermochemical equation for this reaction. So let's just start out with the reaction. So we've got sodium hydroxide reacting with sulfuric acid. Let's just start there. And remember, acids are always aqueous. Okay. And since we're told that this is a sodium hydroxide solution, that's your clue that sodium hydroxide is aqueous as well. Okay, so just as a refresher from Chemistry 20 as well as Science 10, since we have a compound reacting with a compound, what type of reaction this is called is a double replacement reaction. So you could either think of it as your positive ions or your cations switch with your other positive ions or your cations. So what this means is hydrogen likes to be a cation. Sodium likes to be a cation. How I know this for sure is if you look this up in your periodic table. Okay, so hydrogen, yes, it does have positive and negative, but the negative is only for hydrides, and we do not have a hydride in sulfuric acid. We have the positive version here. Okay, another way that you know that hydrogen is your cation in your sulfuric acid is because sulfate is the anion. Same with sodium hydroxide. It likes to have that positive charge. That's how you know it's the cation. Hydroxide, if we look it up here, right there, it has a charge of -1. That's how you know it's your anion. Okay, so I like to just switch cation with cation. Now keep in mind it's the identity of the ion that's switching, and why I say that is because a lot of times people will bring the subscript along for the ride, and that is not the case. That's not what you do. You only switch the identities of the cation. So what I mean by that is, so hydrogen goes to take the place of sodium. That's going to mean I'm going to color code this so you can track where everything's going. We're going to get HOH, which is the same thing as water because water is H2O. We still have 2 hydrogens and an oxygen. Okay, so this is water, which at room temperature is going to be liquid. Now, if we're talking about sodium, sodium goes to take the place of hydrogen. Okay, so I'm going to write sodium and then the sulfate ion. Okay, so I only switched the identities of the cations. I did not bring the subscripts along for the ride. The whole point of the subscripts is only to balance out the compound. So if I look at water, hydrogen I know likes to have a +1 charge, hydroxide likes to have a -1 charge. This is balanced. Okay, now sodium, I know that likes to have a +1 charge, and if I look at my list of polyatomic ions, sulfate likes to have a -2 charge. Okay, so this does not equal 0, or it is not balanced right now. So how I get it to be balanced is I like to call it crisscross applesauce. So you take the numbers, but not the charges for the overall charge, I guess, of your ion. Okay, so this is where the crisscross applesauce part comes from. Okay, I'm just taking the 2 from here and putting it behind sodium. Now, for sulfate, I only need 1 of them, so I don't need to write a number. Okay, and also if I did write a number, that would be very confusing because it looks like we have 41 oxygens here. Okay, so that's another reason why you shouldn't write a 1 there. It just gets confusing. Okay. Additionally, with polyatomic ions such as sulfate, if you only have 1 of them, you leave it like this. If you have more than 1 of them, then you would write brackets and then whatever your number is. Okay, but since we only have 1 sulfate ion in order to balance this out, then we don't include brackets. Okay, so now we need to figure out what the state of sodium sulfate is, so we are going to have to go back to our solubility table, which is on page 6. We're going to find our anion first, so that's sulfate. Now most things with sulfate are soluble, but let's just check our list of exceptions just to see if sodium's there. Sodium isn't there, so yep, it follows under most, so it's very soluble. So that means that this is going to be aqueous. Okay, just in case you were wondering, if you ever had a substance that you found in this last row, what you would put for the state for that substance would be just S for solid, because it's insoluble in water. Okay, but for us, sodium sulfate fits under most, so it's very soluble. Okay, so we've got our skeleton equation done. Now we just need to balance the overall equation here. So we got 2 hydrogens going in. Now, one thing about this is that to make life easier for balancing, I'm going to treat this as my hydrogen and this as my hydroxide. So I'm going to keep my polyatomic ions together for balancing to make it easier on myself. Okay, so when I say 2 hydrogens going in, I am only going to say 1 hydrogen going out. The reason why I'm not counting this hydrogen is because it's part of hydroxide, which I'm counting as one thing to balance. Okay, so 2 hydrogens going in, I'm going to need 2 coming out. Okay, 1 sulfate going in, 1 sulfate coming out, that's balanced. 1 sodium going in, 2 coming out, so I need a 2 there. Now that 2 doesn't just affect sodium, it also affects the hydroxide, so I have 2 hydroxides going in and also 2 hydroxides going out, so everything's balanced now. Okay, so this is just a chemical equation, it's not a thermochemical equation. So what I need to do is I need to take the molar enthalpy of neutralization either for sulfuric acid or for sodium hydroxide. I need to use one of them to figure out my change in enthalpy here. So I am going to do both. However, on a test, I would only expect you to do one of them. Okay? The reason why I'm doing both is just to show you if you've done your previous calculations right, you're going to get the same answer. So again, I'm using this change in enthalpy is equal to moles times the molar enthalpy of reaction, or the molar enthalpy of neutralization. Now, since we already took into account the concentration and the volumes of both sulfuric acid and sodium hydroxide previously in these calculations, that means that these moles come from the coefficient of our balanced chemical equation. Okay, so change in enthalpy, so we have 1 mole for sulfuric acid, and then our molar enthalpy of neutralization for that, I'm going to choose to use kilojoules per mole, so that was negative 121. Okay, so that's how it would look like if you use the information that you had for sulfuric acid. Now, if you used sodium hydroxide, notice that you have 2 moles of it. And then our enthalpy, molar enthalpy of neutralization was negative 60.3 kilojoules. Okay, so I'm going to show this last calculation here. So 2 times negative 60.3 is going to give us negative 120.6. So you could say, well, that is different than negative 121. But seeing as for sig digs, taking sig digs into account, we only need 3 sig digs, that would actually bump this up to negative 121. So you do get the same answer in the end. And I should fix that. There we go. So again, only do one of these for a test, because for both calculations, we're just figuring out change in enthalpy so we can get an energy term for our thermochemical equation, and we get the same answer in the end. So that's why I'm saying you only need to do one of these. All right, so I'm just going to focus on sulfuric acid. So because it's negative, that tells us that energy is being given off from this chemical reaction. Okay, so that means it's a product. So I'm going to write plus, so again, you never write your energy term as negative, 121 kilojoules. So another reminder, you never use molar enthalpy for your energy term in your thermochemical equation. You only ever use change in enthalpy. And then one last thing that I realized that I accidentally missed, this should be written as aqueous here.